So in this lecture we'll talk a little bit more about bonding, particularly covalent bonds, where covalent bonds can be nonpolar or they can be polar. And to understand that, then you have to remember this concept of electronegativity. All right, so electronegativity is basically just a measure of how much an element in a bond wants electrons. And so the values for electronegativity, right, range from 0 to 4. And so if you just remember that fluorine in the periodic table is the most electronegative atom, so any move in the periodic table towards fluorine is going to have increased electronegativity. So as you move basically that way on the periodic table, electronegativity goes up. So you don't have to necessarily know values. I mean, the periodic table will have electronegativity values on it, so you can always look them up. But if we just wanted to compare these two elements, for example, well, this element is to the right of this element, so the element to the right is more electronegative, right? Or if you wanted to compare two elements in a group, right? So as you go across a period, electronegativity goes up, and as you go up a group, electronegativity goes up. So the significance of this is nonpolar bonds. So the difference in electronegativity between the two atoms in a bond is less than 0.4, then it's a nonpolar covalent bond. If the difference in electronegativity is between 0.4 and 2.0, then it's a polar covalent bond. And if the difference in electronegativity is greater than 2.0, then it would traditionally be considered to be an ionic bond. Okay, so if we looked at HCl, for example, and if we can compare it to something like H2, so there's no difference in electronegativity. So if you looked at the electron density in the molecule like H2, it's perfectly symmetrical. Electron density. But in a molecule like HCl, so chlorine's got an electronegativity. These numbers are down or not. It's about 3.0, and hydrogen's about 2.20. So chlorine wants electron density, electrons more than hydrogen. So if you looked at the electron density in the molecule, then it would look something like that, where there's high electron density around chlorine. And low electron density around hydrogen. So one way to represent that is, well, so computer programs can do this now. They can plot electron density maps in a molecule. In this class, we'll simply use these symbols to represent electron density, where chlorine has this symbol, that's red partial negative, and hydrogen this symbol, which is red partial positive. So you express that as partial positive. That means low electron density. And that is expressed partial. So that's the Greek symbol delta. So that's partial negative. That means high electron density. So anytime you have a polar covalent bond, then you would use these. You can use these symbols, partial positive and partial negative, to represent the electron density in the molecule. Right? Why is that important? Because if you understand the electron density in the molecule, then you can predict how a molecule will react. And that is a huge part of organic chemistry. The first few chapters we'll just look at the structure of organic molecules, and after that we'll look at how organic molecules react. And so again, if you know what the electron density looks like in the molecule, you can predict how it's going to react. So if we took a molecule like H2O, so Oxygen's got electronegativity of about 3.5, and hydrogen's about 2.20. So oxygen's going to be partial negative, and both hydrogens will be partial positive. And a molecule like this, CH3OH, so carbon's about 2.5, oxygen 3.5, hydrogen 2.20. So the OH bond is polar covalent. So oxygen's partial negative, hydrogen's partial positive. The CO bond is polar covalent. So carbon is also partial positive. But the CH bonds at the difference in electronegativity, 2.5 minus 2.20 is about 0.30. So it's less than the threshold of 0.4. So those are non-polar covalent bonds. So even though H is technically partial positive, it's so small that we typically ignore it. So we don't assign hydrogens partial positive on carbon because the positive charge density is really, really small. So we just ignore it. Okay, so in this molecule, CH3NH2, one thing that you would have to do on a test is I just give you the molecule and ask you which atoms are partial positive, which ones are partial negative, if any. So nitrogen's electronegativity is about 3, and hydrogen's 2.2, so that's a difference of 0.8, so that's a polar covalent bond. So nitrogen's partial negative, each hydrogen's partial positive, and carbon's partial positive, since carbon's electronegativity is 2.5, so a difference of 0.5. But the CH bonds are not, so these are not. They're not partial positive or partial negative. Okay, so last example, if we took this molecule CH3Cl, if we assign partial charges, so chlorine's going to be partial negative and carbon's going to be partial positive. And again, because chlorine's very electronegative compared to carbon, but the difference in electronegativity between carbon and hydrogen is less than the 0.4 threshold. Okay, so for formal charge, formal charge has a formula associated with it. It's valency electrons on an atom. So oxygen, for example, has 6 valency electrons, right? You get that from the periodic table. And if we subtract the number of lines, the lines is basically the number of bonds. So 1, 2, 3 bonds on oxygen, and then subtract the number of dots. So that's the non-bonded electrons. So it's got 2 dots, so 6 minus 3 minus 2 equals +1. So oxygen's got a +1 charge. And if we did the same thing for hydrogen, it's got 1 valence minus 1 line minus 0 dots. So hydrogen has 0 charge. So each of these hydrogens would have no formal charge. And you don't want to confuse formal charge with partial charge. So if we took the same molecule, if we looked at the electron density map, technically, so oxygen is much more electronegative than hydrogen. So technically, oxygen's partial negative, hydrogens are partial positive. But so partial charges are based on electronegativity differences, and they represent the electron density in the molecule. Right, so oxygen is the most electronegative atom, so it's going to be sucking all the electron density towards itself, so it's going to be partial negative, it's going to have high electron density around it, but that's a totally different concept than formal charge. Formal charge oxygen is +1 and hydrogens are 0, and formal charge is basically just an electron counting tool that helps you draw Lewis structures, nothing else. So it doesn't represent the electron density in the molecule. So basically it just helps keep track of. Helps keep track of where electrons are in the molecule. Okay, so if we do formal charges for these other structures, so oxygen, 6 valence minus 1 line minus 6 dots equals -1. So that oxygen's -1 charged, and hydrogen's 0 charged, so this is HO minus, or hydroxide, if you remember your polyatomic ions. And this, the one we just did, would be H3O plus, it's hydronium. Okay, so for this next molecule, so if we consider this carbon, for example, so 4 valence electrons minus 3 lines minus 0 dots, right? Carbon's got 3 bonds on it, so minus 3 lines. So that would be 4 minus 3 minus 0. So that carbon is +1 charged. And if you do formal charges on everything else, there's 0. So if we took that carbon, for example, 4 valence minus 4 lines minus 0 dots, 0 charge. And that carbon, 4 valence minus 4 lines minus 0 dots, no charge. Okay, so for these, on this oxygen, 6 valence minus 6 dots minus 1 line would be -1 charge. And so that oxygen's -1. This oxygen on the left looks exactly the same as the one on the right. It's got 1 bond and 6 dots, so if the one on the right is negative, so is the one on the left. And the one at top, 6 valence minus 2 lines minus 4 dots is no charge. And carbon, 4 valence minus 4 lines minus 0 dots, so no charge. So that has a net -2 charge. Well, this would be CO3 2 minus. If you remember what CO3 2 minus is, that's a polyatomic ion carbonate. Okay, a couple more examples of this. So nitrogen, 5 valence minus 4 lines minus 0 dots, +1 charged. And then hydrogens are 0. So this would be NH4 plus. That's the ammonium cation. Right, so anytime you're drawing molecules, you should always show non-zero formal charges. Let's get this out of the way. So if we were drawing ammonium, for example, then in this class you should always show non-zero formal charges, so you'd write it like that with a plus on nitrogen. Or if you're drawing hydroxide, you would draw it like that with a negative on oxygen. Sometimes in textbooks you see them wrote like this, and they don't specify where the charges are at. But in this class, you should always show the atoms that have the charge. And again, because it's useful to know how molecules are going to react. Okay, so one more concept in this lecture that we'll cover, and that's what's known as structural formulas, expanded structural formulas, condensed structural formulas, and line formulas. Okay, so if we take this molecule, So that would be what's called an expanded structural formula. It shows all bonds. But it's not a very convenient way to write a molecule because it takes up a lot of space and it takes a lot of time. So we can make this easier to draw by writing the condensed formula. So instead of writing all of the CH bonds out, we can just say CH3. So that's a CH3. So we have a carbon attached to 3 CH3s and then attached to an OH. So that would be a condensed. So that would be a condensed structural formula. Or we could make it even simpler. Since we have a carbon that's attached to 3 of the same things, then we can take those 3 things and put them in parentheses. So CH3 3 times attached to carbon, which is attached to OH. So that would be a condensed formula. So that contains the same information as the expanded line formula does. It's just a lot faster and a lot easier to write. So anytime you see something in parentheses, then so you kind of read molecules left to right, just like you're reading a book. So these 3 CH3s are attached to the next atom. They are attached to that carbon. So if you kind of work backwards, so expand it out to a condensed structural formula, which you show the 3 CH3 separately attached to carbon. And then you can work backwards to the expanded structural formula and take each of the hydrogens and show its bond separately. And then you would have the expanded structural formula. Okay, so we can also write what a line formula for this molecule. So that's what a line formula would look like. So let me clean it up a little bit. So on a line formula, at the end of any line is a CH3. So that's a CH3, that's a CH3, and that's a CH3. And then any break and the line is a carbon atom. So that's a break in the line at that point, so that would be a carbon atom there. So and then when you're drawing line formulas or even these structural formulas, we typically don't show lone pair electrons. You just have to recognize they're there in order for the atom to have an octet. Oxygen, for example, in order for oxygen to have an octet, it's only got 2 lines, so it needs 2 lone pairs to make 80 electrons. So as you can see, I showed the lone pairs there, but then when I moved to here and I moved to there, I just forgot to draw them just because it's second nature to not even show lone pairs. You just recognize they're there. Right, if the lone pair was not there, then the oxygen would have 6 valence minus 2 lines. It would have a +4 charged. And there's no +4 charge showing there. So that tells you the fact that the oxygen has no charge shown, it's neutral. And the only way for it to be neutral is to have 4 lone pair, two lone pairs, 4 non-bonded electrons. Right, because then you have 6 minus 2 lines minus 4 equals 0. So if those 2 electrons were not there, oxygen would be +4 charged, and I would have to show that. So the fact that I didn't put +4 beside that oxygen means it's 0, which means it has 4 non-bonded electrons. Okay, let's take a couple more examples. So I'll show the expanded structural formula. So that's the expanded formula. It shows all bonds, all atoms, and then let's take that and write it simpler so that we can make the CH3 attached to C double bond O, and then we have a CH2, and we have 3 of them in sequence. So we can take the CH2 and put it in parentheses 3 times, and then it's attached to another CH3. Or we could condense this as well, and we could say CH3, CO2, CH2 3 times, CH3. So anytime you see the CO2 like that in a molecule, it probably expands out like that towards a C double bond O, and then the carbons attached. So the carbons attached to 2 oxygens, one of them double bonded and one of them single bonded. Okay, so that would be the condensed structural formula. And if we took this and wrote it as a line formula instead, so when you put your pencil down, that's the CH3, and then draw up to the next carbon, which has a double bond O, down to oxygen, up to and then up to CH2, down to CH2, up to CH2, and down to CH3. Right. So at the end of a line are CH3s, and anytime there's a break in the line, that's a carbon. So that's a carbon, that's a carbon, that's a break in the line, that's a carbon. And then, so when you draw line formulas, you don't have to show H on carbon. It's just understood that they're there. So carbon likes to make 4 bonds, so you need as many hydrogens as possible. You need the number of hydrogens that would make carbon have 4 bonds. So this carbon at the end, for example, has 1 bond showing, so it needs 3 hydrogens to make 4 bonds. If we go to this carbon, so we'll call that carbon 1. If we go to this carbon 2, it's got 2 bonds showing. So that's 2 bonds. It needs 2 hydrogens to make 4 bonds. And the same for this next carbon, it needs 2 hydrogens. Right, to have 4 bonds. Okay, let's take one more example. Let's try again. So it's very common to have rings in organic chemistry. Let's make this an oxygen. Let's make that a nitrogen instead. Okay, so that's an expanded structural formula. So let's take that and write a condensed formula and a line formula. So you don't have to condense the ring. Well, I mean, but we can write the ring simpler. So if we take the ring and simply write it like this, and so those 2 carbons have a double bond between them. This is not a carbon, that's a nitrogen at the bottom. And then we go to 2 CH2s. So I can put those 2 in parentheses. And then we go to a CH that has an OH. attached to it. And then we go to a C double bond O, which has a H attached to it. And so when you draw line formulas and condensed formulas, you always have to show the hydrogens on non-carbon atoms. So you have to show the hydrogens on oxygens, you have to show the hydrogens on nitrogens, but you can drop the hydrogens from carbons. So anyway, that's how we would condense the ring. And since we have two CH2s, all right, we can combine those and put those in parentheses. And instead of sketching out this CH bond, we can just write CH. And instead of sketching that CH bond out, we can just write CH. And let's see, so we could have wrote here, I guess, CH2. So let's do this. And then this is carbon. So that would be a condensed formula. And then let's write this as a line formula instead. So again, we still show the hydrogens on non-carbon atoms, so we got to show the NH. And then CH2 up to a CH2, down to a CH2, up to a CH, right? Which has an OH attached to it. So we could draw that OH up or down, doesn't matter. And then C double bond O, and we don't have to show the H. We could show the H on that, but we don't have to. It's done. You see it done both ways. All right, so that would be a line formula for the molecule. Okay, we'll stop there.